Hi, I'm John Green. Welcome back to our walk through the entire history of the universe from beginning to end. In this episode, we've arrived at the moment when the stars turn on. Katie literally calls it that. Just staggering to me. And we'll also see how the universe became visible to itself. But first, after our last episode, I can't help but ask Katie about free will. I think everyone should be proud of me, actually, that I waited until 4 episodes in to ask about free will. So here's our conversation. So Katie, I was listening to our last episode, and something occurred to me belatedly that I wanted to ask you about. It seems like a lot of this stuff was inevitable. That each thing proceeded from the previous thing, right?
Yeah. I mean, there was a sort of series of events where, it's all just kind of following the same laws of physics once you set it going.
Yeah, that's starting to make me feel a little bit like once you set it going, there was always going to be a galaxy called the Milky Way, not called the Milky Way, but where the Milky Way is, the size and shape of the Milky Way. And it's starting to make me think that there was always going to be a sun, and it's starting to make me think there was always going to be an Earth once we set this stuff in motion. And just to be clear, we didn't set it in motion. And that's starting to make me think, and I'm really hoping you can correct me on this one, that there was always going to be a me.
The thing is, right, like, when you're looking at it from the perspective of now, all you can do is trace back all of the events along the timeline that we have followed. But there were a lot of different places in the past where things could have branched one way or another. Like, it's true that once you set down the primordial fluctuations in the plasma of the hot Big Bang, those kind of have to grow into galaxies and clusters of galaxies, and galaxies have to make stars and planets. But, whether or not they had to make the Earth and us, like there are a lot of things that are just random chaos that come into that. I mean, things like, in the formation of planets, you have collisions between large rocky bodies and asteroids and things and stuff coalescing from the protoplanetary disk. And that could have gone lots of different ways.
So what you're saying is, and I guess what I'm asking is free will still in the equation?
That I feel like that's above my pay grade somehow. I feel like free will is a very human question, and in the work that I do, humans are so insignificant that
no, I'm getting that feeling.
It's not. I wouldn't even know where to begin with that. On the cosmological scale, we seriously don't matter at all, right? But whether or not we feel like we can, make our own little choices in our own little space, that I don't feel is something that I am qualified to weigh in on.
Okay. Now, when you say we don't matter at all, that's a little bit of a stinger for me, I have to confess, because I know that we don't matter much, but don't we matter a little bit? Here's my argument for why we might matter a little bit.
Okay.
We're the ones doing this observing. And that's interesting.
Right. I mean, we matter to our own ability to gather information. That's true.
Right, but we're not affecting the cosmos.
No. There's this thing that I sometimes bring up when I'm talking about dark matter and dark energy and the nature of the cosmos in talks, where, that famous image of the Earth as the pale blue dot, right? So this is Carl Sagan, and they it was Voyager 1. They took a picture of the Earth from billions of kilometers away, and it just looks like a speck of dust. Carl Sagan gave this beautiful speech about how, on that speck of dust, every nation and every powerful ruler and every, king and peasant and, we're all on that little speck of dust. None of us matter. We're not, we're a tiny speck of dust in the universe. I think about that picture sometimes, and then I think about, well, in the bigger picture, most of the matter in the universe is dark matter. like 85% or something. And we're going to talk about dark matter and dark energy later on. But most of the matter in the universe is dark matter that we can't interact with except through gravity. And most of the rest of the universe, if you just kind of add up the energy of the stuff in the universe, is dark energy. And dark energy is this even more mysterious stuff that has to do with the expansion history of the universe and how the universe is expanding and so on. And we don't know what dark energy is, but we can't do anything with it. It's just kind of apparently a property of space. And so if you add up the sort of contribution of both dark matter and dark energy in the universe, in terms of the energy density of the stuff in the universe, that makes up something like 95% of the stuff in the universe is either dark matter or dark energy.
Oh, no.
And so the stuff that we're made of, regular matter, what we call baryons in astrophysics, that regular matter and, electrons and protons and neutrons and even radiation, all of that together makes up about 5% of what the universe is made of. And so if you think about it that way, like the dark matter has the strongest role in the formation of structure in the universe. Dark energy has the strongest role in the evolution of the universe. We're just kind of the sort of window dressing. Like our kind of matter is kind of just sort of along for the ride. Like it's important on the scales of galaxies, but beyond that, it really isn't. And so, even the stuff that we're made of is unimportant in the universe, is insignificant in the universe. Even our kind of matter is kind of an afterthought in the universe in some ways. And so, like the idea that we as humanity can be significant to the universe when even the stuff we're made of is kind of not very significant in the universe, it's very humbling. It really is very humbling.
It's humbling. In some ways, it's liberating, right? Because it also means that, did I ever tell you about the time I ate a sandwich that belonged to the New York Knicks?
No.
So one time I was invited to the New York Knicks locker room by a friend of mine who was a reporter, and there was a big plate of sandwiches there in the locker room, and there were all these professional athletes and everything, and these reporters asking questions. And I don't know if you have been able to gather this, but I'm not a professional athlete or a particularly good question asker. And so I was just kind of hanging back, and I saw the sandwich board, and I took a sandwich. I started eating it, and then the head of player operations for the New York Knicks said, "Who are you?" And I said, "I'm John Green. I'm a novelist and video blogger." And he said, "Those are for the players."
Oh no.
And like all your mortifications, I think about it regularly at night. But with this particular mortification, it's worse because usually what you tell yourself is, well, but they don't think about it. Nobody else thinks about it. It's just something that I think about. But actually, the next time my friend, who was the reporter, saw the head of player operations for the New York Knicks, he said, "Man, I think all the time about your friend who ate one of our sandwiches."
Oh, no.
So what you're saying is that actually that's not very important.
Yeah. I'm saying that none of that matters to the universe. And whatever we do, there's a limit to how much we can screw things up because we have so little power.
Yeah, which is also kind of encouraging, right? Because I don't trust us on any level.
No, not at all. Can you imagine if we did control the evolution of the cosmos?
Oh, God, no. No.
That would be so bad.
Yeah, like if we could agree to the rate of expansion, that would be very bad.
Yeah, exactly.
We would do a terrible job of that.
But again, like it's also sort of inspiring because as you said, we can learn so much, right? And we have this amazing power of knowledge of, maybe we're just kind of observers in this bigger cosmos, and maybe we're just along for the ride, but we know so much about it. We can learn so much about it from looking at the distant galaxies and observing the past evolution of the cosmos and understanding the Big Bang, all of these kinds of things. Like we can learn a lot.
And we have a lot in common with the universe on some level because we're temporary. And everything that we've gathered about the universe is that it's temporary. And everything within the universe is temporary. And this is something that blows my mind every time I think about it. I tend to think of myself as being an observer of the universe. For whatever reason, like my whole life, I've been like somebody who watches more than participates. So I'm not uncomfortable with that idea.
Okay.
But we're not actually observers of the universe because we're the universe. Like, we're made out of the universe. So we're the universe observing itself.
Right. Yeah.
And I find that kind of like lovely and encouraging too, that I'm not separate from this thing that I'm looking at. I'm part of it.
So there's this famous quote by Carl Sagan, right? We are a way for the universe to know itself.
Mm-hmm.
To our knowledge, we are the only part of the cosmos that is studying the cosmos. I mean, it's very possible there's other creatures out there who are learning something about the cosmos, who are doing the same observations, but we can't talk to them. We don't know what they're doing. But we are able to learn that. We are able to study our own past, our own creation through the processes of the cosmos.
Yeah.
I think that's very special, really.
Yeah. No, it's something that differentiates us from rainbow trout.
Yeah.
But we still don't matter in the scheme of things, and so it doesn't really matter that I ate a New York Knicks sandwich.
Right.
How do we hold these competing ideas in our mind, that we aren't very important in the scheme of things, and yet that we are also the only part of the known cosmos that knows much about the cosmos? Things look different when you zoom all the way out than when you zoom all the way in. And so, yes, it is true that we are just creatures confined to a single solar system, confined to a single galaxy, and so on. But we nonetheless matter because we are part of the cosmos seeking to deeply understand the cosmos, and also because we matter to each other, which is quite literally why there is life insurance. And with Policy Genius, you can find life insurance policies that start at just $292 per year for $1 million of coverage. Some options are 100% online and let you avoid unnecessary medical exams. Policy Genius helps you easily compare your options from America's top insurers with just a few clicks. So get peace of mind by finding the right life insurance with Policy Genius. Head to policygenius.com/crash course or click the link in the description to get your free life insurance quotes and see how much you could save. That's policygenius.com/crash course. Policy Genius, because we don't matter, but also we do. What are you going to teach me about today?
I think when we last spoke, the first stars had just formed. We were at cosmic dawn. We had just exited the dark ages of the cosmos, and we were at the point when the first stars were beginning to shine. And those stars may have been very, very massive. They were very different from modern-day stars because they were forming in this pristine gas that had no heavy elements in it. It had nothing that we as astronomers call metals, where we use the term metals to mean everything that's not hydrogen, basically.
Oh, wow.
Which is
that's
kind
helpful. That would be a great moment to rename something.
Yeah.
That would be great to have a new name for that.
Yeah, yeah.
I'll work on that.
It's quite silly. But so before that, there were none of these heavy elements. We just had these big stars forming from this pristine gas. And that time frame was somewhere around maybe 100 million years, maybe a little earlier than that, when the first star formed. We don't know exactly the numbers, but it's somewhere in that range. Those stars formed in, clumps. I mean, generally speaking, stars and galaxies form in clumps because you get a big clump of matter, and that matter sort of has these little variations in it, and those little variations kind of form smaller clumps. The way that things form in the cosmos, usually there are like fluctuations on really large scales, so there will be a big area with a little bit of extra matter, and then there will be little areas within that with more matter, and then there will be sort of larger areas with sort of less matter, and it ends up making things clumpy. So it ends up causing galaxies and stars and things to form in clusters. And so at this point, let's say the first star turns on, right? The first star turns on, it's burning hydrogen into helium in its core. And as it's burning, what it's doing is it's fusing elements in its core, but it's also heating the gas around it. And there's a process that happens when these first stars are forming, when the first galaxies are forming, where it's starting to really changed the nature of the gas around in that environment. So you had this transition from this sort of hot plasma to this cool neutral gas when the universe cooled down after the sort of hot Big Bang phase. So you had this neutral gas, and then stars started to form inside that. But when the star forms and gets really bright and really hot, it sort of ionizes all the gas around it. It creates a little bubble of ionized gas just from dumping so much energy into that environment. Imagine this sort of, there's this kind of dense fog throughout the universe, right? And inside that fog, at certain places, these little lights start lighting up, like street lights in the fog. And around those little lights, it sort of burns these bubbles of ionized gas around those lights. So around the first stars and galaxies, you get these little bubbles of ionized gas. And when that starts to happen, it makes it so that light can kind of pass through and it makes it sort of easier to see through that fog. So that fog of the sort of neutral, dense gas of the Dark Ages, it turns out that fog is kind of opaque to certain kinds of light. It's opaque to visible light, ultraviolet light, because essentially what happens is you shine a light into that dense hydrogen fog, and it'll just kind of excite the hydrogen or maybe ionize it a little bit, but the light will be absorbed by the hydrogen. Whereas once the hydrogen is ionized, then visible and ultraviolet light can pass through because it's this sort of diffuse ionized gas, and it can't excite the atoms anymore. It can't ionize the atoms anymore, and so the light can kind of pass through. And so it makes little regions around those first stars and galaxies transparent to visible light. So when this process first starts, when the first stars and galaxies turn on, each one of them is kind of like a streetlight, embedded in the fog, invisible to the other streetlights, right? Because from each perspective, there's a little light and then there's just fog and you can't see through it. But as this goes on, as more stars form, as more galaxies form, as the cosmic dawn gets going, those bubbles of ionized gas, those bubbles of transparent gas start enlarging, start growing. And so when we visualize this time frame in this phase of the universe, we can make these visualizations, these simulations of how that proceeded. And it ends up looking like sort of this Swiss cheese structure of little bubbles around each big clump of stars and galaxies. And then those bubbles expand until they overlap. And the universe goes from being mostly opaque with little bubbles of light to being sort of fully transparent in the way that we see the universe today.
So the universe became visible over time.
Yeah, visible to itself, yeah.
Wow, beautiful.
And that process where it goes from being mostly neutral gas in the universe to mostly ionized gas in the universe, we call that process reionization.
Oh, that's so disappointing.
I'm sorry.
There were so many opportunities there.
I know. But at least this one is better than recombination because it is becoming ionized again after it had been ionized the first time.
Yeah, no, I get that. I understand it. But what an opportunity to be the visualization, the visual ability, I'd have to think about it. I acknowledge the size of the challenge here, but there's no way reionization is the best term.
Yeah, it is a little bit of a, yeah.
Because you got cosmic dawn right there, and so this is really, it's kind of like, it's cosmic morning.
Yeah.
It's cosmic 10:30 a.m. It's cosmic brunch.
It's when the fog burns off.
Yeah, which is around, for me, here in Indianapolis, usually around 10:30. It's usually when I'm starting to think I could go for a bagel.
Just to recap our discussion from last episode, following the Big Bang as things got less dense and less hot, there was a moment when neutral atoms were able to form for the first time. And this is known as recombination. I'm going to spare you my disappointment in the name they chose here, but I do think they could have done better. Recombination was followed by a long period of time where the universe was mostly cold, neutral hydrogen gas. And that's known as the cosmic dark ages. And then, with the help of dark matter, clumps of this gas started to come together, and this led to the formation of the first stars. This was the beginning of what we call cosmic dawn. And part of cosmic dawn, as Katie just described, was the universe becoming visible to itself by breaking the dense fog of the cosmic dark ages through the process of reionization. But what exactly is reionization?
Katie, I'm going to confess what I really don't like about the phrase reionization. I think I know what ionization is, but it's straining my capacity for high school chemistry a little bit. So walk me through these, we've got these early stars, they're throwing off new stuff, and that's reionizing this gas that's around these new stars.
So neutral gas, in this case, neutral hydrogen, if something is neutral, it just means that the positive charges and the negative charges balance.
Okay.
So in the case of hydrogen, that means it's got one proton in the nucleus, so that has a positive charge, and it has to have an electron orbiting it or bound to it. That's a negative charge. And those charges balance if you have one proton and one electron. That's neutral hydrogen.
Right. And then it gets ionized because somehow in the throwing off of this energy, the electron's no longer bound to that particular proton?
Yeah. So ionization is the process of removing electrons from something. So in the case of hydrogen, if you have a proton and electron bound together, that's neutral hydrogen. If you separate the proton and electron, if you unbind them, then now you have ions. You have positive ions, the protons, and you have negative ions, that's the electrons. And so now you have an ionized hydrogen gas.
And now much more interesting stuff can happen.
Yeah.
Because now, light can pass through and other interesting stuff can happen. And that's why obviously we don't want to pick favorites, but that's why we like ions.
Well, yeah. So ionized hydrogen is transparent to visible light and ultraviolet light. I mean, assuming that it's not super, super dense, it's transparent to this light. There's something here that gets a little bit tricky that bothered me when I was first learning about this, and I don't know if this is getting too technical or not, but when I talked about the hot plasma of the very early universe before the surface of last scattering, before the cosmic microwave background happened, that hot plasma was so dense. So a plasma is just an ionized gas, really. That's all that plasma really means. It's a hot ionized gas. So that hot plasma was made of protons and electrons and helium nuclei and more electrons. So it was just ionized hydrogen and helium and a bunch of electrons and a tiny smattering of lithium and stuff. So that plasma was just ionized gas, just hot, dense ionized gas. But the light couldn't move around in that either. In some sense, that was opaque too because
it was so dense.
Because it was so dense, yeah. And so when that cooled down enough that those atoms were able to join together and make neutral atoms, when you went from that hot plasma to neutral hydrogen and neutral helium, so those electrons were able to find those nuclei, the electrons and the protons bound together to make neutral hydrogen. The electrons found their helium nuclei and made neutral helium. When that happened, that became transparent to some kinds of light. So radio waves could pass through that gas. Even that was a neutral gas, kind of dense. So visible light still couldn't pass through that because it would get absorbed by those atoms. But radio waves could now pass through. So it's funny because when you talk to early universe cosmologists, they talk about the universe becoming transparent when the surface of last scattering happened and the universe became neutral. But then if you talk to distant galaxy cosmologists, they talk about the universe becoming transparent when the universe became ionized again.
Because one group is talking about when it became transparent to radio waves, the other group is talking about when it became transparent to visible light.
Yeah, and ultraviolet light. Yeah. And so it's all about what kinds of light can pass through, what kinds of gases, and it's this kind of complicated process. So at this point, once the gas is a bunch of neutral hydrogen, mostly, then when the stars turn on, it becomes ionized hydrogen again. But first in sort of these bubbles of ionized gas.
Yeah. And then the bubbles expand, and then eventually we have this situation where the whole universe is visible to itself.
Yeah, yeah. And it's visible because it's low density ionized gas, because it's not a hot dense plasma. So there are a couple of really interesting things about that process. One of them is that we're starting to get to the point where we can kind of see that process occurring in some ways. So one way is that when we look at really, really distant quasars, so a quasar, which I think we'll talk more about later, a quasar is it's a supermassive black hole in the center of a galaxy that creates jets of radiation, and it has matter swirling in, creating this really bright glow. Those turn out to be extremely bright objects in the distant universe. So quasars are some of the brightest things that we can see in the universe, and so we can see them very, very far away into the universe. Within the first sort of billion years of the universe, we can see some of these quasars. So sometimes when we look at the spectrum of the light from those quasars, we can see, based on how the light has been absorbed by the gas between here and that quasar, we can see, like, for a certain region around the quasar, the light is not being absorbed very much. So we can see that the light is kind of passing through a little bit right around the quasar. And then we see this other region of the spectrum of the quasar that shows that all of the light was absorbed in that part of space.
So we can see the streetlight and the little bubble around the streetlight, but we can also kind of infer the fog.
Yeah, exactly. And we started to be able to see that a few decades ago, where we started to be able to see that we were looking at quasars that were within that time frame of reionization when the universe was not fully ionized yet, when there was a lot of neutral in the universe. And understanding that transition is really important. And I'm talking a lot about this partially because this has been a big part of the research that I've done personally, has been thinking about how to better understand the epoch of reionization and what happened there, and to learn about that early process of galaxy formation. But if we really understand how that process happened, how the universe went from being fully neutral to fully ionized over that time frame, which was a time frame of probably from around 500 million years to around 1 billion years, somewhere in there is when that occurred, and it took a little while. It wasn't instantaneous. We can use that to learn about what those first stars were like, what those first galaxies were like, how bright they were, what they were doing to the gas around them. We can learn about those early quasars. We can learn about how the temperature of space was changing over time from that lighting up the universe. And we're starting to get to the point where we can use radio telescopes to actually look at that neutral hydrogen gas as well. So usually with a telescope, what you do is you look at a bright thing, right? Like you use a optical telescope to look at bright stars and galaxies. You can use a radio telescope to look at processes that create a lot of radio waves. So things like quasars can make these like bright radio sources in the sky. Pulsars, stuff like that, can make bright radio sources. JWST is looking at infrared light because it's looking at galaxies that are really, really far away, and their light has been stretched out by the expansion of the universe. And I'll say a little bit more about JWST in a moment, because we'll talk about what it knows about these early galaxies. But one of the things that you can do with radio telescopes is you can look at a sort of weird property of hydrogen gas, of neutral hydrogen gas. Normally, the way an atom emits radiation is you have the nucleus of the atom, and then you have electrons going around the nucleus of an atom in sort of energy levels. Right, so they have different energy levels. So there's the sort of lowest energy levels, and then there's the higher energy levels. Just has to do with kind of how the electron is going around the atom. And normally the way that an atom emits light is that the electron will drop from a higher energy level to a lower energy level, and that'll emit a photon. Or if it absorbs a photon, it can go from a lower energy level to a higher energy level, or it can even leave the atom entirely if the photon is energetic enough. I kind of imagine these electrons going up and down and either emitting or absorbing light.
Okay.
With neutral hydrogen, if the atom is neutral and unexcited, so the neutral hydrogen is just a proton with an electron going around it, right? There's another kind of transition it can do, even in the ground state. So the electron is in its lowest energy state. It's just hanging around this hydrogen. The hydrogen is cold and boring. But there's a transition that the electron can do where the electron has a spin, which it's a weird concept because it's not really spinning, but there's this property of electrons that we call spin. Particles have this spin property, which is kind of like if you're spinning a basketball on your finger and it's kind of going around. And the way that we visualize it is if it's going around and around sort of clockwise and the arrow points in one direction, if it goes the other way, the arrow points in the opposite direction. So if you spin the basketball one way, you think of that as spin up. If you spin the basketball the other way, you think of that as spin down.
I do think I need to stop you there because I do not understand. Is it okay for me, in my imagination, as a novelist, to think of it as sometimes it spins right and sometimes it spins left if I just know that that's not true?
Yeah. Yeah.
Whew, thank God.
Yeah. I mean, usually we go with up and down, but it's kind of unimportant.
Up and down, up and down. Great. Okay. Yeah, sometimes it spins up, sometimes it spins down. And if it spins up, it's spinning into a higher orbit or no?
No. So the spin is just a property of the electron. It could be either way.
Okay.
But if the spin of the electron and the proton are in the same direction, or if they're in opposite directions, that changes the sort of energy level of the neutral gas.
Oh. So even though it's a neutral gas in both ways, there are different energy levels based on whether the spin is the same or opposite.
Right, exactly. So if you have just neutral hydrogen with the electron in its lowest energy state, if that electron is spinning in the same direction as the proton, then it has a little bit more energy than if that electron is spinning in the opposite direction of the proton.
Because they're like working together in my imagination.
Sure, yeah.
Yeah, collaboration is more effective than conflict.
Yeah. And because they have different amounts of energy, it means that if there's a transition, if that spin flips, if the electron spin flips, then it'll have to emit a photon. Or absorb a photon if it's going from, let's say the proton is spinning up. If the electron starts with spin up and it flips to down, then it emits a photon. If it goes from down to up, it absorbs a photon.
Okay. All right.
And so it's kind of like energy levels, but they're just these tiny like splittings of the ground state energy level. And because of that, the photon is really low energy. And that photon is such low energy that it's a radio wave.
Oh.
So most of the time when we talk about transitions of energy levels in hydrogen, we're talking about like ultraviolet or visible light.
Yeah, that's what I thought.
In this case, it's a radio wave for that tiny transition, that tiny energy state. And so that's a super, super useful tool because that means that neutral hydrogen, before the universe is transparent to visible light, but when it is transparent to radio light, that neutral hydrogen can make a little bit of radio light. And it can absorb a little bit of radio light. And so what we can do, which is kind of amazing, so neutral hydrogen is just cold neutral hydrogen. There are some stars and galaxies happening, but they haven't affected the whole universe yet. They're just in these little bubbles, right? But that neutral hydrogen can absorb some of the radio light from the cosmic microwave background and flip that spin. And if we tune radio telescopes to the right frequency, we can look at how that neutral hydrogen is absorbing the cosmic microwave background light.
Oh.
And we can see the transition from the neutral gas to the ionized gas by looking at the gas itself, not any of the bright things that are happening, but how that gas is absorbing the cosmic microwave background light.
Wow. Wow.
And this is a really hard measurement to do for a bunch of reasons.
I can imagine. It seems like it would be challenging.
Yeah. And there are a few big experiments, a few big telescope programs to try to do this observation. It's called 21 centimeter astronomy because that radio wave that's emitted when that spin flip happens has a wavelength of 21 centimeters, which is kind of big, right?
Yeah, it's huge.
But because of the expansion of the universe stretching out the light, it actually ends up much longer wavelengths. So you have to tune your telescope to even longer wavelengths. And we should talk about all of that, Redshift, which I'll talk about in just a few minutes. But anyway, the problem is that you're trying to see this little absorption of this cosmic microwave background light from neutral gas kind of, everywhere in the universe. But we live in a galaxy that creates a whole lot of radio waves. And so it's very hard to disentangle those radio waves. It's something like a factor of 1,000 brighter, just the galaxy in those frequencies of radio waves than the signal we're looking for. So it's a really hard measurement to make. But there are some big projects. There's one called the Square Kilometer Array that's a whole bunch of radio dishes, mostly in South Africa and a couple of neighboring places. You make a huge array of dishes in a bunch of different places to try to like bring together the information to look for this transition. There are a couple of projects that are just like a single sort of antenna, basically, and they're just kind of adding up all of the radiation from the whole sky and trying to disentangle this signal through sort of creative processing. And there's one called EDGES, which is one of these single dish experiments. That telescope has claimed to see that dip, that absorption of light, but in a way that seems sort of like too big a signal. And so there's a whole bunch of other telescopes trying to like confirm or rule out that signal. So we're not sure what we've seen yet, but there's an effort to look directly at the gas to see that transition and learn about those first galaxies just by seeing how they messed up the gas they were embedded in, which is kind of an amazing thing.
Wow.
That the idea that we could learn something about just this cold hydrogen gas in sort of the epoch of cosmic dawn when virtually nothing else was happening. I mean, there's even efforts to look at the dark ages. Like, so we're talking about cosmic dawn mostly, where there are some sort of bubbles of light from early galaxies, but you can also look for the dark ages themselves when there are no stars yet. And it's just this neutral hydrogen absorbing the CMB. And in order to do that, though, you have to go to such low frequencies that the ionosphere of our Earth is going to absorb all of that radio light because it's opaque to radio waves at that frequency. And so there's discussions about putting a telescope on the backside of the moon to get away from the ionosphere and to get away from the radio interference of like, FM radio and stuff like that.
Yeah.
In order to observe this signal.
Wow.
It would be a really amazing thing to be able to watch that transition, to be able to watch the cooling gas during the dark ages and those bubbles of ionization forming during the epoch of reionization. To be able to watch that movie would be amazing.
Yeah, and we're talking here about direct observation, not inference, right? Like we're actually, I mean, seeing isn't quite the right word when you're talking about non-visible light, but we're talking about seeing this process happen.
Yeah, watching the evolution of our universe.
So these early stars reionizing the dense fog of the cosmic dark ages allowed the universe to become visible to itself. We have identified certain extremely bright objects in the universe called quasars that are distant enough to be within the epoch of reionization. And there's an ongoing effort right now to witness this key period in the history of our universe. And if we are successful, we can use that to learn about what those first stars and galaxies were like.
Okay, so we've got this reionization happening. The universe is becoming visible, and we're able to at least be on the edge of directly observing this happening. What comes next?
So I've often thought about, like, the only way we're going to see some of those first galaxies or learn something about from some of those first galaxies is with these radio efforts to see that neutral gas, the epoch of reionization, to watch that progress. But now that we have JWST, we're starting to see what really might be some of those first galaxies directly from the light of those galaxies, which itself is kind of amazing, and we're learning quite a lot about what those first galaxies were doing. And I just want to say a little bit about this because it's such an important project, and it's telling us so much, and it's bringing up new complications in our understanding of this epoch of the first galaxy formation, this process of reionization. So let me say a little bit about JWST first. So the full name of the telescope is the James Webb Space Telescope. It's an infrared space telescope. So the reason that it uses infrared light instead of visible light like Hubble or other frequencies, other wavelengths of light, the reason it uses infrared light is because it's really trying to look at some of the first galaxies in the universe. And those galaxies, they were not red. They were not shining in the infrared. They were shining in ultraviolet light and visible light, just like galaxies today are, because they had stars in them that were making a lot of, light across frequencies, but largely ultraviolet and visible light. The reason that it looks in the infrared, though, is because the expansion of the universe has stretched out that light so much because these galaxies are so far away that now the light that reaches us from them is in the infrared part of the spectrum.
It is, as they say, redshifted.
Redshifted, yeah. So as the universe expands, it looks to us like those distant galaxies are moving away from us very, very quickly. And in that process of the expansion, or you can equivalently think of it as moving away and stretching out the light, that light gets stretched out. And so it goes from being ultraviolet to visible to infrared light. And so by the time we get it, it's almost entirely infrared light. And so that's why you need to make an infrared telescope, and you have to put it in space because our atmosphere absorbs a lot of infrared light. And so putting it in space and having it use infrared gives you the ability to pick up light from some of these very first galaxies that formed in the universe. To be clear, they look kind of like little smudges to us, the very earliest galaxies. We don't see a lot of detail, but we see something, and the only reason we see something is because of this effect of distant things looking a little bit bigger when they're distant enough. So we've now been able to see a whole bunch of galaxies that formed within the first 400 million years of the universe.
Okay.
Now, I mentioned that the first stars were probably 100 million years, maybe like 50 million years, somewhere in that range, the first stars formed. So these are galaxies that they have to be made of like the first or maybe second generation of stars, like maybe a little bit more if they're really massive stars and they go through their generations very quickly. But they're very, very early galaxies. They're some of the first things that ever formed in the universe. And there's been this really big sort of discussion in the cosmology community, and some of it has gotten into the press about the fact that some of these galaxies, they just look like they're too big. They look like they're too bright. They have too many massive stars. And it's hard with the kind of understanding we currently have of galaxy formation, it's hard to see how they had time to get that big, right? From the moment the first stars formed to the galaxies having, these huge masses of stars. Like, how did they grow up that fast? Right? How did you make all that matter come together?
Because we know it became easier to make stars once we had a lot of these heavier elements.
Yeah. And just like, getting a whole lot of mass into one place is kind of hard. Like, it takes time to gather all of that mass together and then to turn it into stars. And there's been this kind of ongoing discussion in the literature where we have a bunch of these really high redshift stars. So we call them high redshift because they have this large amount of stretching. Let me just back up a bit. Let me say something about redshift. So when astronomers talk about these galaxies, we usually talk about them in terms of their redshift, which is a number that tells you something about how much the light has stretched. But that number also tells you how much the universe has stretched, like, since that time.
Right, of course.
Okay, so a redshift 1 galaxy, that means that the observed wavelength of the light is twice as big as the emitted wavelength of the light. So that means that the light has stretched
by a factor of 2.
By a factor of 2. Yeah.
I would have called that one 2, but okay.
Yeah, well,
then you can't have a 1.
Yeah, well, the problem is we need today to be redshift 0.
Right. Okay. Yeah, I should. I can criticize your names. What I shouldn't criticize is your math.
Yeah, probably.
Yeah, I should probably stay clear of that one.
What that also means is the wavelength has doubled. Is twice as big since redshift 1, but so is the universe, right? Because the thing that doubled the wavelengths was the universe got bigger. So space has gotten twice as big since redshift 1.
Okay. And so if we're talking about redshift 7, we're talking about the universe being 7 times bigger.
8 times bigger.
Right, sorry.
Yeah, no, I know.
8 times bigger.
8 times bigger than it was at that time. Yeah.
Okay, I got it.
And so some of the galaxies that we're looking at with JWST have redshifts about 10.
Wow.
So the universe is like 11 times bigger now than it was when those galaxies emitted their light. We're talking about, it was a really long time ago, the light is very, very stretched out. So, factor of 10 stretched out. And these galaxies, once we started observing a bunch of galaxies that we thought were around redshift 10 and saw that they were massive and bright, it kind of got a bunch of astronomers worried about, like, how did they have enough time to build up that many stars? How did that formation have time to happen? And so there were a whole bunch of papers written. Some of them got changed because the initial calibration of the telescope gave sort of different numbers for things. And so some of the galaxies that seemed to be really, really high redshift were not quite as high. Some of the redshift estimates were off. But there's still this like tension with our current galaxy models. And it seems like it's something that's resolving just based on, like, the problem is that we just don't have that clear an understanding of galaxy formation. It's actually really complicated. So, I mean, what we've talked about so far is like gravity makes gas come together and forms a galaxy. But the actual process of like how much of that gas sort of gets too hot and puffy and sort of pushes out and slows the formation, how clumpy that gas gets, whether there are magnetic fields involved that affect how the gas comes together, what kinds of stars are forming in those galaxies. So are those stars sort of forming steadily, or are they forming in sort of big bursts where there's a big burst of star formation and then it's quiet for a while? How do black holes fit into this? And we're going to talk about black holes next time. But, each of these galaxies probably has some black holes in maybe a supermassive one at the center, and that changes how these things are forming. So there are all these complicated processes that go on in galaxy formation. And we're starting to have a pretty good idea of how galaxies form in the kind of recent universe. But it was real different back then because the universe was so much more dense, so much smaller, hotter. The formation processes were working differently. Things were just real different back then, in the first 100 million years, the 400 million years of the universe. So JWST is starting to give us a glimpse of that early process of galaxy formation, and radio telescopes are going to start giving us a glimpse of that whole process of like dark ages reionization, probably not dark ages until we get something on the moon, but, reionization. And we're going to start to really understand how those first stars and galaxies formed and lit up the universe and broke apart the hydrogen and created this transparent universe that we can see now, where we can see through that fog and really see the sort of larger cosmos.
So I've read some of these news stories that have come out. Like you said, like papers get published and then a certain number of those papers get filtered into news stories. And it tends to be the sort of more sensational, more like surprising stuff that gets into news stories, I imagine, just like in any other field. And a lot of the news stories I've read are like we have to be wrong about something because there's no other way to explain how galaxies could have been forming this early. And it seems like you're a little less worried about that than the news stories I've read.
Yeah. I mean, some of these stories are like, we have to throw out the Big Bang. No. like there's a lot we don't understand about galaxy formation. There's a lot we don't understand about black hole formation. And I'll talk about how we don't understand how supermassive black holes get so big. Basically, they're kind of different regimes of physics that have different levels of like very clear understanding. Like the idea of gravitational collapse, gas comes together to form clumps, dark matter comes together to form clumps. That's a kind of physics where we're pretty solid on that. We really understand how that works. But once you get to the point where the regular matter becomes important, where galaxies start to form, where stars start to form, that regular matter is just so freaking complicated. like even just keeping track of like Like one of the projects I'm working on right now with some of my students and some postdocs has to do with thinking about how dark matter might have affected those first stars and galaxies. And the short version is that if dark matter were doing something that caused it to create some radiation, then that could have changed the way those first stars and galaxies formed. And in order to do this calculation, like we have to go through these papers with like these giant tables of all of the different kinds of reactions that can happen between hydrogen and electrons, and like all of the energy levels of hydrogen, all these transitions of like hydrogen and then ionized hydrogen and then hydrogen with an extra electron and then molecular hydrogen where there's two hydrogen nuclei bound together. And then you throw in some helium, you throw in deuterium, which is hydrogen with a neutron on it for some reason. And then as soon as you get some heavy elements, then you have whole tables of like opacities and cooling curves. And it's just massively, massively complicated because gas physics is massively, massively complicated. So if I had to choose between saying like, our understanding of the whole Big Bang is wrong or our understanding of the formation of galaxies is wrong, like it's definitely the galaxies, right?
Right. Because it's so complicated and because there's so much that we might not have measured correctly or and everything seems so interdependent too. Like every measurement seems interdependent on every other measurement.
Yeah. And so like there's the modeling is really complicated, the simulations are really complicated, but the observations are also really complicated. Like with JWST, we can get spectra on some of these galaxies. And if you get a good spectrum, then you can really, really say what the redshift is. But if you don't get a good spectrum, you're kind of making some kind of guess about the redshift. So there are just a few of these things that there are sort of lots of knobs to turn in all of these models and a lot of corrections to make with the observations. And so, I think that even though it's a really interesting question, why we're seeing really massive galaxies at very high redshift, it's also not at all a challenge to the story that I've already told about the Big Bang, because all these pieces of evidence we have with the cosmic microwave background and with the sort of evolution of the gas, like that story is pretty solid.
Well, I have to say, it's been very interesting to learn about one of your current little corners of cosmology. And my main conclusion is that your work seems complex.
Yeah. I mean, I think that the problem is, like, I would love to work on, like, a very, very simple, clean, pretty problem, and there just aren't that many of those. So you always start with a problem where you're like, oh, this is really simple. I'm just going to do this, and it's going to be this nice, clean calculation.
Oh,
and then you get into it, and you're like, I have to know all of the energy levels of hydrogen.
Right. The closer you get to the problem. This is very similar to writing a novel, actually. Every time I start a novel, my wife always makes fun of me because she's always like, because every time I start a novel, I tell her, like, I'm going to be done with this in like 10 days.
Yeah.
This is a very simple story that I'm trying to tell. And 5 years later, it turns out that the story wasn't so simple.
Oh my goodness. The number of times I've talked to a collaborator and been like, this will just be a quick little paper. Then, like 3 years later.
Yeah.
Yeah, I mean, I'm sure there are some problems in astrophysics where you can get like a nice, neat little thing that just kind of makes sense immediately. But those kinds of problems are so few and far between. And there are always some kinds of complexity that you have to just deal with. And you have to just like, well, I guess, I'm going to have to calculate that because I don't know if it's going to be important or not until I put the numbers to the page. And fortunately in cosmology, a lot of times we can neglect things. So we call it neglecting something if we decide that there's something that's not important.
I like that.
For example, I was talking about the evolution of structure formation, large-scale structure in the universe, like the distribution of galaxy clusters. When you do those calculations, you can neglect regular matter for the most part because it's just
because it's only 5%.
Yeah, because it's such a small fraction that it's pretty much the dark matter that's governing that process. I mean, even when we do the simulations, so I told you about, you can do a simulation where you take the pattern from the cosmic microwave background and you add gravity and then you see clusters forming. those simulations are generally done with only dark matter.
Oh, wow.
And then once the clusters form, you just sprinkle the regular matter on top of the places where it's really dense. And then you say that's where the galaxies are.
Oh, God.
So.
Oh, wow. Oh, my gosh.
Yeah, so a lot of times you can just, because there are some processes which are just so much more important than others, you can say, look, we're never going to see the difference if we put that number in or not. And so you can just leave it out. And sometimes what gets cut is all of the stuff that we're made of.
So you can neglect not just us, but everything that comprises us.
Yeah. On a large enough scale. Yeah, absolutely.
Oh, my. All right. Well, that took me right back to the beginning of the episode feeling.
Oh, no.
Where I feel suitably small.
But in a good way.
Yeah.
In a liberating way.
Well, in a mostly liberating way. And yeah, I'm never going to be discouraged by being too small. There's no part of me that thinks oh, humans don't have enough power yet.
Right, exactly.
So I'm certainly at a place in my own relationship with humanity where I feel like we are big enough. I would not want us to be that much bigger. So it's good to know that even if we could control all of matter, it wouldn't be that important.
Right. Yeah, exactly.
So there's obviously a lot we can't control in this universe, maybe everything. But we might be able to build a telescope on the far side of the moon and use some of the brightest objects in the universe to witness the beginning of cosmic dawn. And that's something. And maybe we can even determine how the earliest galaxies formed. In a conversation that started and ended with clear evidence of our insignificance in this universe, I still remain in awe of what we can accomplish, one little species on one little planet. Next time, we talk about something I know absolutely nothing about: black holes. I can't wait. This show is hosted by me, John Green, and Dr. Katie Mack. This episode was produced by Hannah West, edited by Linus Obenhaus, and mixed by Joseph Tuna-Medish. Special thanks to the Perimeter Institute for Theoretical Physics. Our editorial directors are Dr. Darcy Shapiro and Megan Modafferi, and our executive producers are Heather DiDiego and Seth Radley. This show is a production of Complexly. If you want to help keep Crash Course free for everyone forever, you can join our community on Patreon at patreon.com/crashcourse.